Good morning, afternoon, or evening. How y'all doing today? Welcome back to Morals Math Corner. Today we're going to learn how to rationalize radical expressions. So let's get right to it. When a radical appears in the denominator of a quotient, you must convert the quotient so that the denominator does not contain the radical any longer. This is a process called rationalizing the denominator. In order to rationalize a denominator containing a single square root, simply multiply both the numerator and denominator by the square of the given denominator. It's pretty simple. Think of this as a helpful hint. The square root of a times the square root of a will always equal a. So when you multiply the radical denominator by itself, the resulting value will equal the original radicand. Why does this happen? Because the square root of a times the square root of a is officially the square root of a squared, which equals a. And that's why anytime you multiply a radical times its exact self, it just simply equals the radicand. So for example, I want to rationalize each expression. I cannot have a radical in the denominator, so I'm literally going to multiply by the square root of 5. Why the square root of 5? Because I need two 5s to pull one out of a square root, so I've got 2 square root of 5 over square root of 5 times square root of 5 is 5. If you need to go the long way, square root of 5 times square root of 5 is square root of 25, which is 5. Square root of 7 divided by square root of 12. Well, one thing you could always do, and I strongly suggest, is first simplify the radicals if possible. This 12 is a 3 times 4, but the square root of 4 is 2. So this is really square root of 7 over 2 times the square root of 3. Now I can go ahead and multiply by the square root of 3, which would give me the square root of 21 over 2 times the square root of 3 times the square root of 3 is 3. So that would equal the square root of 21 over 6. Please note, if you wanted to start by multiplying the square root of 12 to both sides, to both the numerator and denominator, you will still get the same answer, but you're going to have to simplify a lot more. So I strongly suggest to please simplify radicals before rationalizing if possible. Okay. Over here, I'm going to multiply, of course, both the numerator and the denominator by simply the square root. Don't I have to multiply by 5, Moro? No, I do not. I'm getting rid of the radical. I can always have a 5 down in the denominator, but I cannot have the square root of 2. So this is going to equal 4 times the square root of 2x over 5 times, please remember, the square root of 2x times the square root of 2x. When you multiply the same exact radicals, it equals the radicand. So this is going to equal, now I'm going to reduce, 2 goes into 4 2 times, so I've got 2 square root of 2x over 5x. Some people are going to say, oh, can't I simplify this x in the radical with the x down here? Absolutely not. 100% you cannot do that. Whole numbers with whole numbers, radicals with radicals. All right, let's continue. Rationalizing a denominator which contains an nth root, not a square root radical, works the same way. The goal is to multiply both the numerator and denominator by an nth root that creates a perfect power of that nth root so that the denominator does not contain a radical any longer. I know that may be a little bit weird to you now, but I promise it's going to make sense in a few seconds. Tip. I've been repeating myself a lot on this one. Know your perfect squares, your perfect cubes, your perfect fourths to easily create perfect powers of given nth roots. For example, If we had to rationalize a quotient which contained a cube root of 4 in the denominator, we would multiply both the numerator and the denominator by a cube root of 2 and not 4. Why, Moro? Let's go ahead and show you why. The cube root of 4 really breaks down into the cube root of 2 times 2. The question is, how many more 2's do I need to pull a 2 out of a cube root? Well, Moro, I need one more cube root of 2. So therefore, I would just be multiplying the numerator and the denominator by a cube root of 2, giving me the cube root of 2 over the cube root of 8, which equals 2. Magic. It's not magic at all. 1, 2, 3 2's in a cube root come out as a 2. So that's the goal when you have an nth root. Let's practice. I have the cube root of 6 here in the denominator. I'm going to go ahead and need 2 more 6's to complete that perfect cube. So I'm going to multiply the cube root of 6 squared to both the numerator and denominator, giving me the cube root of 36 over the cube root of 6 cubed, which equals, you got it, 6. So I've got the cube root of 36 over 6. All right, got the cube root of 5 over 18. I'm going to personally separate this to the cube root of 5, and I'm going to break down that 18 to make my life easier. I know that 18 comes from 2 times 9, which is a 3 times a 3. So why do I do this? Well, think about it. I've got 1, 2. How many more 2's do I need to pull out a 2 from a cube root? I need 2 more. So I'm going to multiply by 2 squared. I've got 2 3's. How many more do I need to get that third 3 to pull out a cube root? I need 1 more 3. So I'm going to multiply that to both the numerator and the denominator to make my life easy. So I've got the cube root of 5 times the cube root of 12, so that's the cube root of 60, over the cube root of, check this out, 2 times 2 is 2 cubed, so that comes out as a 2. 3 squared times 3 is 3 cubed, so that comes out as a 3. So I've got the cube root of 60 over 6. Let's go. You know that was easy. I know you're saying that to yourself. Let's go. We can do this. Okay, I'm going to first break this down. I'm going to try to simplify as much as I can. So I know that this is 6 over the 4th root of actually 2 times 2. And then I've got 3 x's. Okay, so I'm going to multiply here by what? How many more 2's do I need to complete the 4th root? I've got 2. I need 2 more. How many more x's do I need to complete the 4th root? I've got 3. I need 1 more, which I'm going to multiply to both the numerator and denominator. So this is going to give me 6 times the 4th root of 4x over, check it out, 2 times 2 is 2 squared, times 2 squared is 2 to the 4th. The 4th root of 2 to the 4th is 2. Boom. X cubed times x is x to the 4th. The 4th root of x to the 4th is x. I can simplify. 6 divided by 2 is 3. So my final answer will be 3 times the 4th root of 4x over x. And you're done. Let's go. All right. Next, conjugates are expressions as so. Square root of a plus square root of b, or the square root of a minus square root of b. These guys are conjugates. Whenever I have radical polynomials, all I need to do is change the sign in the middle to make conjugates. So for example, 1 minus the square root of 5 and 1 plus the square root of 5 are conjugates. 3 plus square root of 2 and 3 minus square root of 2 are conjugates. You simply change the sign of the second term. to make a conjugate. Okay? Now let's see what happens when you multiply conjugates. Let's remember this old skill from before. It's called the difference of squares. Remember that if you have a plus b times a minus b, you're always going to get a squared minus b squared as your answer. Where this comes from, first term, which is a squared, minus second term, which is b squared. Okay? If you remember that, then you can do the following. When I go ahead and multiply 5 minus square root of 7 times 5 plus square root of 7, which are conjugates, this is a difference of squares. So I'm literally going to take my first term, which is 5, and square it, minus my second term of square root of 7, and literally square it. Remember that when you square a square root, they cancel. So this gives me 25 minus 7, which is 18. 6 minus square root of 12 times 6 plus square root of 12. This is a difference of squares. First term squared minus second term squared. That equals 24. It's that simple. Now, if you want to go even deeper, I set this up for you here. If I have a plus square root of b times a minus square root of b, it's always going to equal a squared minus b. In other words, first term squared minus second term squared. Okay? If I have it the other way, a minus square root of b times a plus square root of b, same thing. First term squared minus second term squared. If I have the square root of a plus b times the square root of a minus b, same thing. It's a difference of squares. First term squared minus second term squared. If I have square root of a minus b and square root of a plus b, same thing, difference of squares. First term squared minus second term squared. Let's practice. Sometimes the denominator is a sum or difference involving radicals. If the radical expressions are in the denominator, you can rationalize the denominator by multiplying the numerator and denominator by what we just learned, the conjugate of the denominator. For example, I want to go ahead and rationalize this because I cannot have radicals in the denominator. So I'm going to multiply by the conjugate. And I find the conjugate by simply changing the sign of the second term. So now I'm going to distribute. So I've got 3 square root of 10 and 3 times square root of 2 times square root of 2. Square root of 2 times square root of 2 is 2. So 3 times 2 is 6. And then, my friends, first term squared, that's 5. Minus second term squared, that's 2. You're done. 3 square root of 10 plus 6 divided by 3. Please remember always that this is the division property of distribution. So this is going to give me square root of 10 plus 2. Sorry, that was my calculator that fell on the floor. My bad. And there you have it. Okay, let's continue. I need to rationalize this denominator, so I'm going to multiply by the conjugate. All right, so let's get it. I've got 2 square root of 7 times square root of 3, so that's 2 square root of 21. 2 square root of 7 times square root of 5 is 2 square root of 35. Square root of, now in the bottom, this is a difference of squares, so first term squared minus second term squared, and you're done. Now, some people are going to want to go the long way. You can go the long way, you will still get the same exact answer. Remember the distribution property of division. This negative 2 gets divided to both this term and that term, rendering me with negative square root of 21 plus, no, minus, because a positive divided by a negative is a negative, minus square root of 35. Let's go. All right, a couple more. I got 4x divided by 3 minus the square root of 6. I'm going to go ahead and rationalize by multiplying by the conjugate. And again, the conjugate you find by simply changing the second term sign. So this is going to distribute, giving me 12. I'm sorry about that. That's going to be 12x plus 4x times square root of 6. Remember, you can't multiply a whole number with the inside of a radicand. And now here I've got a difference of squares. First term squared minus second term squared. So I've got 12x plus 4x square roots of 6 over 3. Please remember this is the distribution property of division. Divide that 3 to both terms, giving me 4x plus 4/3 x square roots of 6. And there you have it. All right, last but not least, got to go ahead and rationalize because I cannot have a denominator with a radical. So I'm going to multiply both the numerator and denominator by my conjugate. You got it. So now I'm going to go ahead and FOIL. 1 times 2 is 2 plus square root of 8 minus 2 square roots of 8 minus square root of 8 times square root of 8 is 8. That will equal negative 8 minus plus 2 is actually a negative 6. Negative 8 plus the 2. And then 1 square root of 8 minus 2 square roots of 8 is negative 1 square root of 8 over, we have a difference of squares here. So first term squared minus second term squared. That will give us negative 6 minus, this square root of 8 can be simplified to 2 times 4. Square root of 4 is 2, with a square root of 2 left over, divided by negative 4. That negative 4 must get divided to both terms, giving me a positive 3/2 plus a square root of 2 over 2. Remember, you can pause, rewind, and rewatch. Hope you learned a lot. Thanks again. Now you know how to rationalize denominators. Take care now. Come back anytime. Bye-bye.